Good afternoon, everyone, and welcome to this first set of OBIWAN guest lectures. We will start with an introduction to the OBIWAN project by our coordinator, Professor Joris Thibaut from Ghent University. He performed his PhD studies at Ghent University on single-event microkinetic modeling of hydrocracking and hydrogenation. In 2003, he went to IRCE Lyon in France for a postdoc on high-throughput experimentation. At present, Joris is Senior Full Professor in Catalytic Reaction Engineering at the Laboratory for Chemical Technology at Ghent University. He is heading the Catalytic Reaction Engineering Research Group, comprising about 15 junior researchers. They actively investigate a variety of large-scale industrial reactions, and more particularly the rational design of the corresponding catalysts, as well as of the reactors in which these catalysts are employed. Professor Thibaut is also coordinator of eCoduct, a Horizon Europe project in the framework of electrified catalytic reactors. Joris, the floor is yours.
Okay, thank you, Elisabeth, for the introduction. And indeed, with this first OBIWAN event and lecture, it is my pleasure to give some indication, to give some explanation on what the OBIWAN project is exactly about. So OBIWAN is situated in the area of biogas valorization, and the first idea then, or the first thing to understand, is where the biogas is coming from and what kind of composition it has. So the main constituents in biogas are methane and CO2, and those are the ones which we will aim to exploit to turn into valuable chemicals within the project, within the purpose of, within the context of OBIWAN, that will essentially be methanol. Biogas has an important production capacity in our region being the north of France, Wallonie, and Flanders. And what makes it effectively unique is that biogas is a resource which in fact is one of the only bioresources from which the availability increases with the population density. Thinking, for example, because of the fermentation of the sludge coming from wastewater treatment plants. If we look throughout Europe, then biogas is the clear winner in the implementation of biogas plants is Germany, as you can see from this figure, and even more from this one. Followed up by Italy, but also France is as such doing quite well in numbers of plants. Belgium, of course, as a smaller country, is a little bit further, but still is still having a non-negligible number of plants available. And if we see that evolution in the development of the total biogas set against the total number of biogas plants, we see that also capacities as such are increasing. Some further facts and figures on biogas overall. Well, worldwide, Europe is a frontrunner in biogas production, so it is very well suited for us to focus on further valorization of it, not just to use it for its calorific value, but to try and do something better with it. Percentage within Europe stem from the data that were already present on the previous slide. So you see how clearly Germany is the largest contributor. Up to half of the biogas produced in Europe is produced in Germany. But we are good runners-up with France being here. Belgium is not mentioned here, but with the increasing production of biogas, there are certainly possibilities, and we are in a good stage. So the evolution is like the following. In 2023, global production volumes equaled about 45 billion cubic meter per year, of about in the energetic equivalent of 270 terawatt hour per year, from which about half is coming from Europe. Um, some further facts and figures have to do with the production values over the year, and then we see the major increases that are there, so making it relevant to look for further applications and valorization. And that's essentially what we want to do within the OBIWAN project. So we start from biogas, with as main constituents methane on the one hand, CO2 on the other hand. The purpose in the first instance will be to separate those two molecules, to have the CO2 and the methane separately. Aiming at the further processing of the CO2, what we want to do is to then chemically split the methane into hydrogen and solid carbon. And that is done via a process denoted as methane pyrolysis. Um, and that will deliver us the hydrogen, which we then can use to hydrogenate the CO2 into methanol, which then are the two useful products coming out of the OBIWAN process, methanol and solid carbon, which can serve, and then mainly the methanol, can serve as a production basis for sustainable aviation fuels, for farming applications, for chemical raw materials, whereas the solid carbon is a component which can be used for car tires, for example, but also within the context of gas cleaning, that solid carbon is quite relevant. And well, the feedback or the carbon cycle is then with, for example, exhaust, CO2 or waste, which can be fed towards biogas production, such that in the end, the carbon we are discussing about here is effectively renewable carbon, and that we have a closed carbon loop with the carbon that we are using. Um, So what OBIWAN will allow us, what a successful OBIWAN implementation will allow us to achieve, is a reduction of greenhouse gas emissions by avoiding emissions on the one hand, and by transforming greenhouse gases, because both methane and CO2 are greenhouse gases. Methane even up to a few 10 times more than CO2. So transforming those gases into valuable products. That's you could say, the technical objective. Of course, there is also the program objective from the Interreg priorities, which is to contribute to the transition towards a circular economy. The development of innovative technologies to support adaptations to climate change, decrease of pollution on land, in air and water, and also contribute to the recycling of waste. So the innovations that will be brought by OBIWAN are, which we are aiming at, because of course OBIWAN has essentially started at the end of the last year. Is on the one hand to focus on the biogas production and have the ideal production, the ideal composition for our further intended transformation into chemicals, which should be about 60% methane and 40% CO2. To accommodate in this composition both seasonable and substrate related variations. To also properly simulate the process and the intricacies related to this process, such that we can achieve in the end a stable biogas production, both in terms of production rate and gas composition. Those are the innovations related to the biogas production, but of course we also want to further produce chemicals and a component which can be used as a feedstock for sustainable aviation fuels. So the crucial steps in there will be the catalytic methane decomposition or methane pyrolysis into solid carbon and so-called turquoise hydrogen, which is gaining popularity right now a lot as a means to sequester carbon, as a means of hydrogen production without simultaneous CO2 production. It will result in high quality hydrogen production, but the quality of the solid carbon so far is typically a bit suboptimal when aiming at good hydrogen quality. But it will be a challenge to optimize the quality of both. That will be set by OBIWAN. The particular reactor used for the pyrolysis will be an electrothermal fluidized bed reactor, which will allow us to deliver the required heat for the endothermic methane pyrolysis reaction, to deliver that heat by renewable electricity, such that also from that energetic aspect, OBIWAN is contributing towards renewability and circularity. So other aspects are purification and separation processes to be developed for biogas and the CO2 hydrogenation towards methanol. But more detail on that will follow in the presentations which are to come, and will also follow on the occasion of next lectures. So who is the project consortium about? Being maybe a bit impolite and starting with myself, we are from Ghent University together with Kevin van Geem. We will be working on this with myself in the role as coordinator. Then from the north of France, and you could say the southern part of the north of France, we have Chaoyong Liu, André Paus, and Thierry Ribeiro. From these joint institutions here, who will mainly work on the biogas aspects. Then from Wallonie, there is Certech with Benoit Karthuizer, who will mainly work on the separation aspect. And from Lille, there is the CNRS with Andrei Kodakov and Vitaly Ordomsky, who will mainly work on the CO2 hydrogenation. And we also have some associated partners who will follow up and contribute to this. All activities are categorized, structured in accordance to 4 work packages. So 2 which are on the management and the communication and training. And then the other 2 more technological ones, with the focus on the biogas and the separation, biogas production and separation, and then work package 4 on the chemical processes. Fine. So I would also like to take the opportunity to acknowledge, of course, the Interreg program for the funding. Also the provinces of Oost-Vlaanderen and Wallonie for co-funding that has been received. And of course our own institutes who also as such contribute with some co-funding.
Our first guest lecture today will be given by Julien Estagier. He is currently a project manager at Certech, which is a research center based in Senef in Belgium. He has an engineering degree from CPE Lyon in France, as well as a PhD in chemistry from the Savoy University. Julien worked for 3.5 years in the Kill Research Center in Belfast in the United Kingdom under the supervision of Professor Ken Seddon, where he developed ionic liquid systems for the capture of CO2 from natural gas for the oil and gas industry. At Certec, Julien is part of the chemistry team and industrial processes on different topics related to process.
Today we will speak about the purification of biogas. So that's mainly an introduction about it because it's a 45 minutes presentation, and that's a quite big topic. So what we did is that we put most of the general concept about it, and we put all the references that you need on the presentation. So if you want to go further into this topic, what you can do is to check in the literature or contact us, so you will have more. So maybe one good thing we should do to start is to present us actually, so you can know why we are part of this project and what we are doing in it. So CERTEC is a research institution based in Senef, as Elisabeth said, so it's in the French-speaking part of Belgium. And our job is actually to support companies, to help them to develop new process and new product, and to behave actually as a R&D partner. So we are a research center which is expert in chemistry, and that's quite a good place to be. I'm in Belgium for chemistry. I just take the map of the north of France and Belgium region because we are speaking about an Interreg project, OBIWAN, which is related to north of France, Wallonia and Flanders, and both on all this region are very strong in terms of chemistry. So for example, in Flanders, you've got about 66,000 people who are working in chemistry. So that's mainly in the region of Antwerp, also in Ghent, but it's a very strong economy. That's the same in Wallonia, where chemistry represents about 1/4 of the industrial employment there, with about 100,000 people with direct and indirect jobs. So that's a very strong economy for us. And that's why we've got a lot of people and a lot of company to support. Considering the Interreg region from the north of France, that's also very strong in terms of chemistry, with about 45 plus thousands people who are working on the topic. And what we should say as well is that it's really SME intensive. I mean, you've got a lot of small and medium companies who are working on this topic. So that's very good for them to have an institution as us that can support them in their R&D, because they can't invest obviously as much in R&D as bigger companies. So at CERTEC, we've got 3 main domains of activities, which are quite related, for some of them, to gas purification. For example, we've got one business unit which is called environment, which is related to everything related to air quality of air, with a strong interest of gas purification, VOC, smell and odors. We are working also on material science. So for us, material science is mainly polymer science, formulation of polymer, but we are also working on different sort of inorganic materials. So for example, today we'll speak about activated charcoal. That's something we are working on at CERTEC as well. And Benoit and myself, who are involved in the project, are part of the chemistry and industrial processes team. And our job is to optimize processes from the industry. Actually, they come with a process, and we try to check what we can make better, and for the in the better case, we try to intensify the process at all. So you can see on the right hand side the different market we are supplying at CERTEC. So chemistry is sort of everywhere. So we are supporting a broad range of different industries that can start from real pure chemical industry, but we are also working with the transport industry, with the food and packaging, plenty of different things. And actually, since the beginning of the century, we have worked with almost 1,800 different companies. So that means that we've got a very large portfolio of customers, which are not only working on chemistry, but also on a lot of different domains. So if we go back to the topic of today, which is purification of biogas, maybe I could start by just giving a definition of biogas. So what I did is more or less the same as what students are doing at the very beginning. I just went on Wikipedia and checked what the biogas means. And as I want to go a little bit further, I also take the real definition from the European Environment Agency of biogas and try to check what it is. So according to Wikipedia, biogas is a gaseous energy produced from raw material, such as agricultural waste, manure, municipal waste, or, for example, wastewater wastes. And it's produced by anaerobic digestion using different organisms, anaerobic organisms and methanogens, into a bioreactor. So you are producing a source of energy from waste. If you check to the definition from the EEA, a biogas is a gas which is rich in methane, so you've got a little bit of chemistry here, and it is produced by fermentation of animal dung, human sewage, of crop residues in an airtight container. So that means, again, it's an anaerobic system for the production of it. Biogas fuel do not usually cause any pollution to the atmosphere because when we are producing the methane and the CO2, it's in a restricted area, so we don't release it in the air. And because they come from renewable resources, they have great potential for future use, especially in Europe, where we don't have that much oil and gas. If compared to other regions, it can be a good addition for our feedstock of energy. So if you check on the left-hand side this time, and it's a graph I took from the International Environmental Agency about biogas. It starts from raw material, organic material that you can transform using a digester into a gas composed of methane and CO2 that you can either upgrade, which means separate, and then you can use it and burn it to provide energy. So considering the feedstock, it's highly dependent on the region you are considering. So as Joris said, Europe is the first player for the production of biogas in the world. And for us, biogas mainly comes from agricultural resources. So that can be from plants like crops, and it's mainly from residues of crop. I mean, we do not compete with food, and that's major part of the biogas we are doing in Europe are from crops and for animal manure. So that can be cattle, pigs, poultry, and sheep. All of that represent about 75% or 70% of the biogas we are producing in Europe. If you consider, for example, the United States, the biogas is of a totally different origin, as it's coming mainly from organic waste and also for water treatment. So when you do water treatment, when you go on a wastewater plant, water treatment plant, you've got a kind of solid, semi-solid organic material that is full of organic compounds that you can use to generate biogas. That's really important because depending on the nature of the feedstock, the property of the gas you will have at the end of the day can be very, very different. So when you start from the feedstock, what you want to do is to transform it into a biogas. So I just did one slide on how to do biogas because that's definitely not our expertise at Certec, and the team from UTC Compiègne is working on that for the OBIWAN project. So you will probably have a lecture later on in the year that will deal with this subject. But generally, that's a biological process, a four-step process. So you start for your mixture of starting material, which are generally polymer like carbohydrates or fats, protein, these kind of things. And what you want to do first is to reduce the size of this big particle by cutting it into smaller molecules via an hydrolytic process. And then you want to transform them into molecules that you can use for methanogenesis. So that's a two-step acidification. You end up with acetic acid and hydrogen that you can transform into methane and carbon dioxide by methanogenesis. So what you have at the end of this process is a gas composed mainly of CO2 and CH4, plus a sort of solid liquid phase, like a slurry, which is called a digestate. So that's quite interesting because generally you know that with the biomass, what the peasants are doing is that they are putting that on the field to enrich their soil, but you can also use the digestate instead of the biomass to enrich the soil because it contains quite a lot of interesting minerals like nitrogen, potassium, calcium, and also nutriments that are useful for the soil, so like metal like zinc, copper, or iron. So today we'll deal mainly with the gas phase, okay? So that was already explained by Joris, but if you consider biogas, it's mainly composed of two gases, which are methane and carbon dioxide. So for the proportion, I already said that really depends on the nature of the starting material, plus on the process you are doing for the synthesis of the biogas, but that generally a majority of methane and carbon dioxide as a 60-40 proportion. So speaking about methane, which is one of these two components, it is generally referred to as natural gas because most of the methane we are using every day is coming directly from the ground. I mean, it's not coming from the biogas. You use it all the time. I mean, you use it as fuel. For example, when you start to use your stove at home, you are burning methane coming from that natural gas. It's not only used for us, for people at home, but it's also highly used in the industry. So, for example, in the chemical industry, it's used to to provide the energy to steam boiler that will generate the electricity for the chemical plants. So that's one of the reasons why the war that happened in Ukraine was so impactful for the German chemical industry, because they had less natural gas to generate the energy of their companies via the steam boiler. So that's a very important gas, not only for people at home, but also for the industry. And it's considered as an energetic fuel because it has a very high heat value, because with 1 kilogram of methane, you can generate about 55 megajoules. So that's very important. And if you compare it to another energetic fuel, very, very, very strong and very famous, which is hydrogen, it generates less energy per unit of mass. But if you consider as a unit of volume, it's better, as it's provide more energy per meter cube than H2. So that's very valuable to use CH4 as an energetic fuel. As a drawback, you can see as well that methane is also very bad in terms of global warming, because it's responsible of 1/3 of the total global warming of today. And its warming potential is 80 times greater than the one of CO2, according to the UN. So that means that even if you release a small amount of methane, you will have a very strong effect on the greenhouse effect on the Earth. So that's the reason why when you generate biogas, it's very important that you keep it confined and you don't release it accidentally in the atmosphere. So the second gas which is generated during the synthesis of biogas is CO2. So everybody knows about that. It's the usual suspect in terms of greenhouse warming effect. It's a gas which is totally oxidized. It's extremely stable, quite difficult to transform it, possible but quite difficult. And as it's fully oxidized, it doesn't burn at all. I mean, the heat value of CO2 is 0 megajoule per kilogram, 0 megajoule per meter cube. You count it as you want, but it does not burn at all. So if you have a mixture of methane and CO2, CO2 will not take part into the heat capacity of the gas. It is also a very well-known contributor to the greenhouse effect. So in most of the process, what you have to do with the CO2 you are generating is to capture it, and then either to store it, generally in the ground, or you can also try to valorize it by transforming it into molecule with higher value, and that's what Andrei will speak about after my talk. So if you consider biogas, it's a mixture of CO2 and methane. So methane is a very efficient fuel, CO2 is not at all. So when you've got mixture, you've got intermediate heat values. So for example, if you consider another way to measure the heat value, which is a lower heat value of methane, is roughly 50 megajoule per meter cube. And if you've got a biogas containing only 45% of methane and 55% of CO2, the lower heat value drops to 16 megajoule per meter cube. So you can still burn it. It's still used in some case directly for burning, but it will be much less effective in terms of energy generated per unit of volume. What you can do if you want is to upgrade this biogas by removing either all CO2 or a big part of it, and you will increase obviously its heat value. But it's not that much that is produced this way. So for example, today biomethane, so methane separated from the CO2, is only 0.1% of the natural gas demand, which is about 3.5 million ton oil equivalent. As we say already, Europe is the first producer of biogas in the world, but we are just upgrading 10% of it into biomethane. So we are mainly burning the biogas we are producing as it is, and just a small part of it is converted in biomethane. However, if you want to valorize it in non-energy applications, it's probably better to separate it, because if you want to do chemistry, you always prefer to work on pure material than on mixture that you don't really control. Plus, the legislation is more and more stringent, so that can change the thing as well. So at Certec, we will work as well on the separation of CO2 and CH4, but that's not what we want to talk about today, because we will speak more today about the purification of the biogas. Because actually I lied a little bit when I say that biogas is composed only on methane and carbon dioxide, because it contains also a lot of different impurities that can have a very strong impact on their use, on the process you want to do with this biogas. And that's what we will discuss today. So I'm sorry, if it's a little bit small, but that's a table I took from a publication from Werknes or from the Netherlands, a quite recent one, when it describes the composition of biogas depending on its origin, so on the starting material you are using. So you can see that you've got very different composition, and that's this composition will vary a lot. You will have some chemicals like hydrogen sulfide, nitrogen, oxygen, ammonia, or siloxanes that can be present in your biogas. For example, in sewage treatment, you've got high amount generally of siloxane that you will have to treat, and all the time, this kind of pollutant can be very impactful and can be quite nasty for your system and for your processes. So I took just the major impurities you can find and tried to explain why it's bad for your processes. So first one, and probably the worst one, is hydrogen sulfide. First thing is that it's a highly odorous chemical. It smells like rotten egg. You smell it instantly, even at very low concentration, like 0.0008 milligram per meter cube, you start to smell it. Not everybody can smell it, but people who are quite sensitive to it will smell it. And not only is it bad smelling, but it's also toxic by inhalation. You can have headache at very low concentration, starting to 0.008 ppm, and it goes to very strong neurological effect. Actually, this gas is labeled as fatal by inhalation, and it's considered as a nerve poison. So you will really have to control it in your gas. It's not only hazardous for health, it's also hazardous for the environment. So, for example, it can react with the humidity you've got in the air and starts to create acid rain in the world. So if it's created corrosive species, that can also be problematic for your pipelines, that can be problematic for your catalyst, it can poison catalyst, it can kill your adsorption process. So that's really something you want to remove for your biogas prior to use. Second impurity you find in biogas is ammonia. So once again, you've got an issue with bad smells. Even if the detection limit is higher, from 5 to 53 ppm, you will have a smell of urine. So that's not also something very pleasant. If you are cooking something and it starts to smell like this, that's not something you want to have in your kitchen. It's harmful to health, even if it's not as bad as H2S. And more importantly as well, it tends to kill the anaerobic bacteria you are using for the digestion process. So you will decrease the efficiency of your process. You will decrease your yield if you've got too much ammonia generated. If released in the air, it can oxidize into NOx, so nitrogen oxides, during the combustion process, which is a problem. That's one of the reasons why some cars are not allowed anymore to go in city centers. It can generate smoke, acid rain, and is also harmful to health. And it poisons quite a lot of, it can generate some corrosion. It can also poison some catalyst, all these kind of things. That's just the last impurity we will discuss today. The first one is water. So obviously water is not toxic, and that's something we need to drink every day to feel well. But as we want to use biogas to generate energy, we want to use biogas as a fuel gas. It's not very nice to burn a wet gas. So you need to remove water, otherwise it will not burn very well. Plus, water tends to accumulate in pipelines, and that can be problematic, especially in regions like here in Belgium or in north of France, where it can be quite cold. You don't want to have potential freezing in your pipeline. That can be problematic in terms of chemical engineering, and it can react with other pollutants present in the biogas, like ammonia or hydrogen sulfide, to generate acid rain or corrosive species. As for nitrogen, once again, it's not toxic. You've got 80% of nitrogen in the air, but it decreases the quality of the biogas and can be toxic for the bacteria during the anaerobic fermentation. You've got also siloxane. So siloxane are quite problematic because during the combustion process, this molecule can transform into species like silicon oxide or quartz. And in fact, that's sort of glasses. So that's the same as if you are generated glass into a motor, into an engine. So that got very strong abrasion properties, and that can destroy your motor very, very, very quickly. You've got then over VOC, so a large run of small molecules of VOC. I won't go into detail because that will really depend on the nature of the starting material, and you've got a too large run of it, but these molecules can be toxic. They can affect the material you are using, like elastomers or plastic. And when you burn it, when you're doing the combustion process, you can form small particles like soot. And these particles either generating during the combustion or already present in the biogas can be also problematic for different pieces of equipment as they tend to plug things or just to stick to adsorbing system. So that's also something you will need to remove. So now we'll describe different methods for the purification of biogas. I will probably describe more things about H2S because that's the most problematic compound you will find in biogas. Generally, you want no more than 10 ppm as your kitchen stove and definitely less than 500 ppm in your combustion engine. And there's generally four main methods that you can use to remove the H2S from the biogas, either by chemical and physical adsorption. So you've got adsorption methods, absorption methods that we sometimes refer to as scrubbing, and we can do membrane separation and precipitation. So as I was not certain of the audience of today, I just put one slide about the main differences in between adsorption and absorption. So adsorption consists in trapping a compound on the surface on a specific of a specific solid. So the molecule have a good affinity with one surface, one solid, and they will stick on their surface. If you consider absorption, that will solubilize in the bulk of the material, in the bulk of a liquid, and the impurity will have more affinity with the liquid, so the impurity will remain in the liquid phase, while the gas, which is not very soluble, will go through. So considering adsorption, that's a surfacing system. So what you want to have is a very large specific surface. The larger the surface, the better it is, and as well as a good porosity. So if you've got a good porosity, you've got a larger surface, that's good, but you need a porosity that fits the size of your the molecule you want to trap. You've got different sort of adsorption. You've got what is called physical adsorption. So the molecule of impurity of a pollutant will stick to your adsorbent by weak physical interaction like van der Waals or even ionic interaction. And you've got what is called chemical adsorption. So you've got some chemistry that happen on the surface. You will create chemical bonds and you will transform the gas you want to remove into other species. So generally, chemical absorption works best. So you can trap more pollutant. The problem is that at some point you will have to recycle your adsorbent. You will have to release this gas. And as you will have in this case to break a chemical bond, you will have to provide more energy. So you capture more gas, but it's more difficult to release it during the cycling. So once again, you have to choose your system. It's a trade-off in between the two. So considering adsorption, that's quite well known. That's suitable for a wide range of flow rates in between 10 and 10,000 meter cube per hour, and for a wide range of pollutant concentration in between 0.1 and 8 gram per meter cube. That's generalities. But historically, if you go to companies, generally that's done at smaller scale that can catch generally up to 200 kilograms of sulfur per day. And what people do is that they generally have a scrubbing of the majority of the H2S using absorbent, and then they do the adsorption of on the solid support. And as you do adsorbent, as you stick the pollutant on a solid molecule, at the end of the day, you will have to change it because it will be totally covered with the pollutant and it will start to lose its activity. So for H2S, there are two major adsorbents that are used. It's activated charcoal and iron 3 oxide or iron 3 hydroxide. In terms of activated charcoal, you can use either pure activated charcoal, so that's pure physical adsorption. And in this case, you can trap up to 10 to 20 kilograms of H2S per meter cube of adsorbent. Or you can use activated charcoal, which is impregnated with another species. So this other species can be, for example, potassium iodide, potassium permanganate, carbonate. And this molecule will react with H2S and oxygen, and we help to and H2S will react in presence of this molecule with oxygen to generate sulfur. So that's what you can see on the right-hand side. So that's a small movie I took on the website from Norit, which is a supplier of activated charcoal. So at the beginning of the process, the charcoal is totally black, and you add some more and more hydrogen sulfide. You generate more and more sulfur, and at the end, the charcoal turn into yellow, which is the color of sulfur. So that using activated charcoal, which is impregnated, you can go to much higher uptake in terms of H2S and go up to 120 or 140 kilogram of H2S per meter cube. Problem will be the recycling, because when it's stuck with S2, you will have to remove with sulfur. Sorry, you will have to remove the charcoal and change it with a brand new one. Second adsorbent that is very often used is adsorbent consisting of iron 3 species. So that can be either iron 3 oxide, Fa2O3, or iron 3 hydroxide. So in this case, you've got a chemical adsorption, you've got a chemical reaction, and you will transform this iron oxide hydroxide into iron sulfide. That's endothermic reaction. You tend to do it at moderate temperature in between 25 and 50 degrees, and for a quite long residence time, 1 to 15 minutes can be relatively long. And generally, you use this kind of process to remove the last amount of H2S that is present in your gas. So you start with a gas with a low amount of H2S, like 100 ppm, and using this kind of system, you can remove about up to 99% of the remaining H2S. Thing is that in this case, your gas must be quite dry and without particle in it. Otherwise, water tend to stick on the surface on the iron 3 and will decrease the efficiency. At the end of the day, you can even regenerate the material by oxidation. Using oxygen, you will go back to iron oxide, iron 3 oxide, but it's a really exothermic process. You will really have to control the temperature, and after a limited amount of regeneration, the surface will be totally covered by sulfur, so you'll have to remove the material and to change it. Anyway, that's a commercial system. You can find, for example, 3 different examples of commercial system, and you've got plenty of others. So that's it for adsorption using H2S. So that's just one table. So that's written quite small, but you can have the references, so you can look into it for more detail. And all the time, that's mainly activated charcoal and some iron 3 species, some iron 3 processes. So on the right-hand side, you can see a traditional process. So you start from the biogas that goes into a traditional liquid scrubber, and afterwards that's adsorbed on different type of charcoal in this case. So that's a two-way process. So on one way, you've got the adsorption process. So you put the H2S on the charcoal. When it's fully saturated, what you can do is close the system, and from the other side, start to flow some gas to remove the H2S, which is blocked into adsorbed onto the charcoal. Sorry. So that's for adsorption. Now for absorption, so what you use are scrubbers. So the concept I already explained. You just want to bubble your gas into a liquid. You want the impurity to be highly soluble in this liquid and your gas not to be. So your gas will bubble through and your impurities will remain in the water. When the liquid phase is totally saturated with the impurity, you can remove those just by stripping with a gas, a neat gas, or just by decreasing the pressure. So actually, for the capture of H2S, water is a very, very good scrubber, because hydrogen sulfide is 80 times more soluble into water than methane. So what you do is you just bubble your gas into water and you remove quite a large amount of the H2S present in it. What you have to consider as well is to have a regenerative loop to remove the H2S that tend to accumulate into water, not to have a consumption of water which is too high. So you can use water, but you can use other type of solvents. So you got a lot of organic solvents that are used for physical capture of H2S. So for example, ethylene glycol, propylate carbonate. And the most common system is probably the Selexol process, which is now owned by UOP, which consists of a mixture of polyethylene glycol ethers. So that's the same concept of water. You're just trapping your impurity and your methane goes through. So that's purely physical absorption, but you can also have physical absorption. So in a liquid phase, you have species that will react with H2S and transform it. So one example is a redox process in between iron 3 and H2S. So in this case, you generated iron 2, and to prevent the precipitation of the iron 2, you want it to remain in the solution so you can retransform it in iron 3 at the end of the day. You will have to have a K-latent like EDTA. So it's a mixture of EDTA and iron 3 that can capture chemically your H2S. Again, an industrial process. Some commercial systems are available for this kind of purification. You've got membrane purification. I won't insist that much on it because we are not expert on membrane purification at Certec. That's definitely something you want to work on and develop our expertise during this OBIWAN project. So what you want to do in this case is that your gas will not go through the membrane and your impurity will go through. So you've got various effects to do that. You've got solution diffusion effects. So one gas can solute and diffuse into the membrane while the other cannot. And the second is by size exclusion effect. So you've got small holes, small pores into the membrane, and the bigger gas cannot go through and the smaller gas can. Problem is when you consider CH4 and H2S, they are quite similar in terms of size, so size exclusion is not that good. When you use a membrane, what you want to prevent is to have a poor selectivity. You don't want some CH4 to go with your impurities, to go through the membrane. Otherwise, you will lose a lot of money. What you are selling is the CH4, so if you lose half of it in your membrane process, you will lose half of your money. So, plus, last thing to consider is that H2S tend to have impact on the quality of the membrane. So after a while, you can have plasticization of the membrane or aging of it, so the quality of the separation can decrease with time, and you will have to change the membrane at the end of the day. So that's, again, you can refer to this publication by Rao et al. And he described the 4 main polymers that are used for membrane separation, which are cellulose acetate, microporous polymers, and polyethylene oxides. And last system that is used to prevent the formation of H2S. So in this case, it's not really to separate H2S from the biogas, but to prevent this formation and to trap it during the digestion process. So what you do is during the digestion, you are adding some species, either chemicals or biological in your system, and you will generate new species that will tend to precipitate in the digester. So that can be iron 2 chloride, iron 3 chloride, iron 3 or iron 2 hydroxide, and in this case, you are generating either iron FAS or directly sulfur 0 that will tend to precipitate in your digester. Thing is that you can't have very high purification in it. It's considered as a partial removal of the H2S, and you can reach maximum 100 ppm at the end of the day, but not much more than that. So we will have anyway to implement a second step for the purification of the biogas. So that's sort of a conclusion for the purification of H2S. So that's a different method you can use. So adsorption using iron 2 or activated charcoal, absorption with different scrubbers like water or other membranes, or precipitation in the digester. So for each process, you've got advantages and drawbacks, and depending on what you want to do and the quality of your biogas at the beginning of the process, you will have to select with care what you want to do. Second thing you want to remove from the biogas is water. So, as I say, water is problematic because you don't want to burn a wet gas. And actually, during the process of purification, you even tend to add water to your biogas. So, for example, when you do water scrubbing of your H2S, at the end of this process of desulfurization, you can have up to 5% weight of water into your biogas. So you really need to assess this problem and to address it. And the same kind of methodology can be used compared to H2S. Actually, you can have some absorption system considering glycols or calcium 2 chloride in solution, or you can use like adsorption using desiccants like silica gel, molecular sieves, and this kind of thing. So that has the exact same advantage as described previously and the same kind of issue. You can also design your adsorbent or your absorbent to be multitasking. So for example, to remove water, CO2, and H2S, and all these kind of things. Second way to remove water is more a physical process. So you can either transform water gas into liquid water by condensing or by cooling the system, either by pressurization or decrease of temperature. That's really effective, but that's quite costly in terms of energy. You will need quite a lot of energy to proceed. Other gas to be removed would be oxygen, nitrogen. So that's mainly because of regulation, and generally, for example, the low acceptable level of O2 for biomethane is 0.5%. You don't really have any reason to have oxygen into your biogas at the beginning because it's coming from an anaerobic process. And generally, this kind of molecular gases are coming from leaks in your systems. So if you've got leaks, you've got air that comes in, and with air, you will have nitrogen and oxygen. You will have to be extremely careful about these leaks because it's quite difficult to remove these molecular gases. Generally, it's extracted by pressure swing adsorption, either by using activated charcoal or molecular sieves, but this system costs a lot in terms of energy. So to remove a gas that is introduced by a leak, you will have a high cost in energy. So it's really something you can prevent prior to the purification system. So considering ammonia, as I said at the beginning of the talk, ammonia is quite problematic because it tends to inhibit the anaerobic bacteria during the fermentation, the digestion process, So that's not really purification of biogas because you want to remove it prior to the formation of the biogas. So that's not really something we are used to do at Certec because it's more biological generally process than chemical process, and we are chemists and non-biologists, but there are different sort of methods. The first one is bioaugmentation. So that just means that in your mixture during the digestion, you have different sort of bacteria to hinder the formation of the pollutant. You can do more classical reactive adsorption. So you use some solids which are impregnated with acids. So your ammonia will react with the acid to form ammoniums, and ammonium are salts, so they will not go into the gas phase. Or you can just strip the ammonia continuously during the formation of the biogas. So that's the first three main way to prevent formation of ammonia. So last chemical molecule I want to talk about are siloxane. So siloxane are chemicals which contain silicium, oxygen, silicium bond. So actually it's quite easy to remember because the name is composed of the name of these three compounds. So it's Sil for silicium, Ox for oxygen, and An for alkane. Some can be volatile, so you will form them, you will have them into the biogas. So you've got different form of structure for this siloxane. They can be either cyclic or linear, and depending on their structure, you will have different way to remove them from the biogas. The amount of biogas you have can be very different depending on your starting material, on the biomass you are using. So for example, if you're starting from sewage plants, you will have generally quite a large amount of siloxane in it. So you really have to treat it because, as I said already, they will transform in gas that can kill your reactor and your engines. So for example, if you are using microturbines, you have very stringent regulation on the amount of siloxane you can have it, and you can't have more than 0.003 milligram per meter cube of siloxane into your biogas. So once again, you've got different way to do it. The most common one is adsorption. You can use the usual suspect like activated charcoal or silica gels. One of the problem you have with the siloxane is that they tend to polymerize into the pores of the material, and by doing so, they will block the pores, they will block the surface, and the adsorption system will not work very well for a very, very long time. So that's especially present when you are using activated charcoal. So that's one of the reasons why some specific material have been introduced. Specifically for the capture of siloxane. So especially activating alumina. So the fact is that these aluminas, larger pores, And in this case, you don't have the polymerization of the siloxane into the pores. So you don't have the deactivation of the catalyst, which is as strong as with activated charcoal, and you've got quite a lot of commercial activated alumina that are specifically designed for the capture of siloxane. However, it works very well for the cyclic siloxane. If you consider the linear one, which are of smaller size, the pores of this alumina are maybe too big to trap them very, very efficiently. So you've got also, in this case, the chemical absorption that can happen. So you can trap this siloxane using different sort of solvents. Once again, you can try to catch it with the Selexol, with these dimethyl ethers of polyethylene glycol from the Selexol process. You can use also methanol, that's very efficient, but the energy you need, especially for the regeneration of the solvent, can be problematic, and you also need to pressurize it and to cool and warm it up depending if you want to release or trap the siloxane, and that can cost money. And second thing is that you are using chemical solvents, you raise quite a few issues in terms of health and safety. It's toxic. Some solvents are toxic, like methanol. You've got flammability things you have to consider for your process. So that's working well, but you got to think about your chemical engineering when you implement this kind of purification process. Second way to do that is using a physical system. You can use condensation of siloxane by cooling or pressurizing it. Same system as what we are using with water. You don't need solvent in this case. That doesn't cool that much in terms of solvent, but you need also to have quite a lot of energy to do it. So it's quite energy intensive. So I'm over with the chemicals. Just one slide about the particles, because that's also something which is problematic. You really want to remove it from the biogas to prevent the release of this particle in the air during the combustion process. Plus, this particle can plug the different engines. So you've got a lot of engineering process that can help for the removal of particles. Either you can use cyclone filters, and you use the centrifugal forces to stuck the particle on the outer side of the cyclone and then remove it. You can use different sort of filters. However, when they are totally filled with particles, you just have to remove it and change them. Or you can use like metallic candle that they are behaving like sort of physical sieves, and then you will remove the particle using that. So that's more or less all for me. I just have a few slides for conclusion. So maybe the first one, so that's a table I took from quite a recent publication, and that described the OPEX of all these different techniques that you are using, of some of these techniques, sorry, that you are using for biogas purification. And that's maybe one message you really have to consider, because every time you will add a new purification step, that will cost you money. That will cost you money in terms of capex, because you will need to build the unit for the purification. But that will also cost you in terms of OPEX, because the operating costs can be quite high. So for example, if you're using, according to this table, traditional impregnated activated charcoal for the removal of H2S, that will cost you 60,000 euro for treating about 1,000 meter cube per hour of biogas. So every time you add a new purification step, that costs you money. So that's one of the reasons why you really need to know well your biogas. You need to know what you want to remove. You need to know your spec, not only in terms of application, but also in terms of legislation. And you need to stick to it. You don't need to purify it too much, because it will cost you quite a lot of money. One thing I didn't say as well is that, as I say, you need to know the nature of your biogas. You need to investigate it. It will really depend on your process for the production of the biogas and on your starting material as well. So that requires quite a lot of insight in terms of analytical technique, chemical or physical analytical technique, to determine what sort of impurities you have in your biogas. So once again, that costs money as well. But that's money good invested, because if you know what you want to remove, that will save you money at the end of the day. So just as a conclusion, now I show you some way to remove the impurity in the biogas. Something we didn't talk about, and that will be the main topic of a future lecture by Certec in the scope of the OBIWAN project, would be for the upgrade of biogas, which means that we want to remove the CO2 from the CH4. So at the end, we've got a biomethane, which is pure CH4 and pure CO2. And with this CO2, you can, if you want, try to improve it, upgrade it, valorize it by transforming it in higher value molecules. And that will be the talk of Professor Kodakov just after me. So to finish, I just want, as Joris just said, but that goes as well for me, to thank all the people we are working with. First, University of Ghent, Certec, CNRS, UTC Compiègne, Catalysti, Euramaterial, Greenwind, Valbium, and Unilassal, and as well as the different institutions that are paying for this work. So the European Union via the OBIWAN Interreg program, Flanderen, as well as Wallonia. And I thank you very much for your attention.
Our second guest lecture will be given by Professor Andrei Kodakov. He graduated from the Moscow State University in 1987, received his PhD degree in 1991 from the Russian Academy of Sciences, and his habilitation degree in 2002 from the University of Lille. Currently, Andrei Kodakov is a senior CNRS research director in the UCCS CNRS laboratory in the University of Lille. His research interests cover catalyst and reactor design aspects of conversion of fossil and renewable feedstocks by thermo and photocatalysis, reaction mechanisms, and kinetics, in situ and operando techniques. Andrei, the floor is yours now.
So, I will present chemical conversion of CO2, because CO2, as Julian was presented earlier today, is a major component of biogas. So the idea of our project is to produce both methane and CO2 and then convert all this product to obtain valuable products, for example, such as methanol. So in my presentation, I will just give an overview of possible CO2 hydrogenation options which we may have. So first, I briefly introduce my laboratory. So my laboratory is unit of catalysis of chemistry of solids. It's a joint laboratory of University of Lille, CNRS, National Center for Scientific Research in France, Central Lille Institute, University of Artois. In our laboratory, so it's located in Villeneuve-d'Ascq, very close to Lille. We have about 100 researchers. We have more than 80 PhD students and more than 20 postdoc. And our laboratory produces more than 200 publications per year, and we present about 200 communications. So now I give more information about our research group, which is called CATSUS-CHEM, which is focused on sustainable catalysis. So what is especially our topic of our research? It's a catalyst and process designed for C1 chemistry. So we're interested in the valorization of CO2, CO, methane, methanol, formaldehyde, and formic acid. And we're actually targeting conversion using thermo and photocatalysis. So research topics is CO2 upgrading, methanol mediated hydrocarbon synthesis, Fischer-Tropsch synthesis, synthesis of methanol, dimethyl ether, methane activation. On the slide, I also showed some picture of reactors which using to test the activity of our catalyst and photo and thermocatalysis. So we see high throughput reactors, which will be also used in this project for methanol synthesis. We have batch reactors. We have also reactors which are using photocatalysis, for example, for also batch reactors. Also, we're using a lot of operando reactors for operando experiments to follow the structure of the catalyst under the reaction conditions. Now I will go to the topic of my presentation. So it's CO2 conversion. First, of course, which are motivation for CO2 conversion? First, I would say environmental motivation. So we know that the amount of CO2 in the atmosphere is increasing every year. So I checked yesterday the numbers for March 2025. So it's about 428 ppm, so it's increased pretty fast. If you see in July 2023, it was 423. So it's almost 4 ppm increase in 1 year, almost 1 year and a half. So it's the first motivation for CO2 conversion is environmental. And then the second is economic motivation, because in Europe we have so-called carbon permit for the companies. It means that the companies have to pay for the amount of CO2 which they produce and emit to the atmosphere. So we see that if we compare, say, 5 years ago, 10 years ago, I would say maybe 9 years ago, the price of carbon was relatively cheap. So we're talking about 10 euro per ton. But say since 2022, the price of ton of CO2 which can be emitted to the atmosphere increased from 10 to say I would say 70, 100 euros. So it's seven times, almost 10 times. So in fact, there is also economic motivation for companies to deal with CO2, to try to valorize the CO2 instead of emitting them to the atmosphere. So actually, we talk about CO2 is a part of energy transition. So this information I found in the Financial Times website. So which is defines the energy transition. So we need to switch to renewable feedstock, renewable energy to improve process efficiency, circularities, carbon capture and storage, and carbon capture and utilization. So if we talk about CO2 chemical conversion, so this is relevant to carbon capture and utilization. So if we talk about transforming CO2, the most important, I would say, is thermodynamic aspect, because carbon dioxide has a low energetic level and very high thermodynamic stability. So, and there is kind of a dilemma, I would say, when we're trying to transform CO2. So there are two kind of options. First is functionalization and energy. So we need to add to CO2 some energy. Also try to obtain some useful products. So, for example, if we want to produce polycarbonate using, for example, epoxide and CO2, of course, maybe it doesn't. We don't need a lot of energy. However, in this case, we are quite limited to the number of products. So in most of process, when we try to convert CO2, we need to add some energy to the system. So it's called vertical approach, when we take CO2 and produce a valuable product which has higher energy. So you see hydrocarbons, maybe alcohol, esters, amine, so and other products. So it means in this case we have to talk about CO2 reductive chemical conversions. And there are two options, two strategy in this area. First is single step CO2 reductive conversion. What does it mean? We take CO2, we take water, and from CO2 and water we produce products. So it's kind of artificial photosynthesis, I would say, with CO2 and water and produce. So of course it's maybe interesting, but now this single step CO2 reductive conversion has very low maturity. So we are limited to the laboratory experiments and we cannot go to higher technological level. So there is another step, another strategy is so-called two-step CO2 reductive conversion. When we first produce green hydrogen, typically by electrolysis from water using renewable energy, and then we take CO2, we take hydrogen and green hydrogen, and by hydrogenation we produce valuable products. So advantages of two-step CO2 conversion, that it has higher productivity and higher maturity. So even now we can design a pilot demonstration, even industrial units for two-step CO2 reductive conversion. And if we talk about CO2 hydrogenation, of course, we can obtain different products. For example, first we can just obtain syngas, which is important intermediate, and syngas can be used for different applications, for energy, for chemistry. Then we take methane, methanol, formic acid, formates, dimethyl ester, light olefins. So, of course, in the presentation today, I will give an overview of our research. So, in the synthesis of formate, dimethyl ester, and light olefins from CO2 and hydrogen. Of course, in all these processes, was mentioned at the beginning of my talk, we are limited. Of course, the main important is, of course, thermodynamics and also kinetics, because most of these processes are catalytic. So we need to develop catalysts which improve the kinetics of chemical reactions. So first about formate. So CO2 hydrogenation to formic acid. So why, the first question, why formic acid is a valuable product? First, of course, there are several, so the slide show different applications of formic acid. So it's insecticide, so de-icing agent, can be used in synthetic chemistry, and also it's important for hydrogen storage. For example, that we can, now there is also a big challenge how to store the hydrogen. So, and why formic acid is good? Because it can react with hydrogen, produce formic acid, and then we can decompose formic acid and produce hydrogen and CO2. The advantage of formic acid is we don't produce CO. For example, if we store hydrogen in methanol, by decomposition of methanol, we can obviously produce hydrogen and CO2, but also it's very difficult to get rid of CO, which is very bad, for example, for fuel cells application and also for chemical synthesis, for example. However, the production of formic acid from CO2 is a thermodynamically difficult reaction. So especially it's exothermic reaction, but the problem is entropy. So entropy, so for that, if we take equilibrium conversion of CO2 and hydrogen to formic acid, we'll have very low yield. So the goal is now how to improve thermodynamics. So one of the esterification, so we not produce formic acid, but produce esters. And also we can produce not, for example, formic acid, but different salts or complexes with amines. And if we produce complexes with amines, this is significantly improve the thermodynamics. So currently, formic acid produced by methanol carbonylation. So this is the slide shows this diagram. So it's very high pressure and also temperatures using alkaline solution. And then we have two options how to transform, to obtain formic acid. So first we have to do, we produce not formic acid, but methyl ester. Then we need to do hydrolysis of the methyl ester, or maybe formamide hydrolysis. So there are two options, but in both cases it's multi-step process, which requires significant energy intensity and also use of alkaline solutions. So what we develop in our group, it's so-called new types of catalyst. It's called solid micellar catalyst. So it's the catalyst which is present a composite of M41 silicas and in this case ruthenium. So, and by optimizing the synthesis conditions, we can obtain so-called single site of ruthenium in this composite. So, and this actually this single site ruthenium in this composite actually play a role of active sites in methanol synthesis and formate synthesis from CO2 and hydrogen. So we investigated the structure of this catalyst using different techniques. Here the results of X-ray absorption, which we obtained in a synchrotron in Paul Scherrer Institute in Switzerland. So what we can see here is that in our catalyst, so here, for example, there is EXAFS data, it's ruthenium MCM free samples. And what we can see is that we really we don't have, say, ruthenium oxide nanoparticles, that we have really single site of ruthenium. So also we confirm this by doing high resolution TEM. So here's the high resolution TEM data. So we can see that we have very nice structure of MCM41, which is a porous, so mesoporous materials, periodic mesoporous materials, very defined structure. We have this, you can see the pores. And also we can detect using atomic resolution ruthenium single site. So by combination of different technique and also DFT modeling, which was performed in collaboration with Professor Sez in Ghent University, we identify the nature of active sites for synthesis of formate from CO2 and hydrogen, which showed on this slide. So actually we use this site stabilized by surfactants and also by OH groups and also by the structure of MCM41 silicas. Now we measured the activity of the sites in formate synthesis from CO2 and hydrogen. So we use batch reactor, which is shown here. And the analysis of formate, which are produced, were performed by using NMR spectroscopy. We tested, so here the typical conditions. So the temperature is 90 degrees, typical temperature 90 degrees, and we produce, so there is about 30 bars of CO2 and 20 bars of hydrogen. So, and we can do it with water and without water. So I'll show next slide why it's important. So, because in many publications before our work, people prepared usually very diluted solution of, you can see here, diluted solution of formate. So of course, if you prepare very diluted solution, it's difficult to use these solutions because we need to concentrate formic acid. So our method produce high reaction rate, which is characterized by turnover numbers. And also the advantage of this method that we can produce a relatively concentrated solution of formic acid, which can be used for formate for different applications. Now I go to the second topic of my presentation, dimethyl ester. Dimethyl ester is important carbon neutral fuel. So typically it's used for fuel application and can be used in conventional diesel engine with modified fuel injection. So we have very high potential market. It have high cetan number, which is important for diesel engine with quiet combustion and also very clean burning. So if you compare conventional diesel with dimethyl ester doesn't produce any particles, any smoke, which is of course a better advantage to compare to conventional diesel, which contains a lot of aromatics, and can be also distributed using LPG infrastructure, which is already available, and it doesn't have any sulfur compound because it's produced from can be produced from CO2 and hydrogen, which already can be clean and doesn't have any impurities. So if we talk about CO2 hydrogenation to dimethyl ester, you have, so there are several reactions which is involved. So I showed on this slide which we have. So first we have CO2 and hydrogen, which reacts to give methanol and water. And then methanol can be also obtained from CO2, CO. And then we have methanol dehydration to produce dimethyl ester. And of course, very important reaction, which we always have to take in mind, is a reverse water-gas shift reaction of CO2 and hydrogen produce CO and water. So, and in the reactor, when we're producing dimethyl ester from CO2 and hydrogen, we have all this reaction taking place at the same time. So for that, when we design the catalyst, a kind of complex catalyst, so-called bifunctional catalyst, because we need metal function, or say can be a metal function for hydrogenation of CO2, say to methanol. So, and when we hydrogenate CO2 to methanol, we should avoid production of methane, because if produce, for example, a lot of methane, it's not desirable product because that doesn't have very high value. Also, we should avoid production of CO, basically. So, because CO is also not very desirable product for this reaction. And then we have, when we produce methanol actually will react on acid catalyst. It's called dehydration reaction, give you dimethyl ester. So in fact, the catalysts have several components. So, and that, of course, what is important is which catalyst we use for methanol synthesis, which catalyst for dehydration, and how these two components interact, which is between which each other during the reaction. So typically for in this work for synthesis of methanol, we use copper zinc catalyst, which is the most studied, actually one say the best catalyst for methanol synthesis, which has this characteristic which I show on the slide. So we have copper metal particles, which is located in zinc surrounded by zinc oxide particles, and there is synergy between metallic copper and zinc oxide, which allows to produce methanol with high selectivity. And then we use acid component. We try first to use a conventional crystalline zeolite. Two types of zeolite we tested was SAPA 34 and ZSM5. So they have different actually pore diameters, different morphology. So, but both of them, so ZSM5 is a more acid zeolite than SAPA 34, but both of them produce loud dehydration of methanol to dimethyl ester. Also, in collaboration with Professor Valchev, we try so-called embryonic zeolite. Embryonic zeolite means zeolite which contain larger pores than conventional zeolite, actually zeolite which is not fully crystallized. So, however, they have several advantages like accessibility and diffusion of molecules. And using this zeolite, we're able to improve the productivity of dimethyl ester in the bifunctional catalyst built from copper-zinc catalyst and zeolite. And in addition, so first step was developing of the catalyst, but then we need to think about the operation. And the challenge in synthesis of dimethyl ester from CO2 and hydrogen cells thermodynamics, because thermodynamics is not very favorable. So how we can improve thermodynamics? So here I just wrote the equation: CO2 and hydrogen, dimethyl ester in water. So the idea was to remove water from the system by adsorption. For example, if we remove water during this reaction, we can shift the equilibrium to dimethyl ester. Here on the left part of the slide, there is dependence on the composition of the reaction mixture and concentration of dimethyl ester as a function of the steam of the water which is present in the reactor. For example, if we increase the amount of water, increase the amount of steam, you see that the amount of dimethyl ester decreases. So if we want to increase the amount of dimethyl ester, we should remove water from the system. So, and here's this setup which first used to do this work. And actually this work was performed at a part of Interact project in collaboration with TNO, it's a Dutch research institution. So here, for example, we use, in order to remove water from the reactor, we used 3A zeolite, which is zeolite is well known for high absorption capacity for water. So, and what we did, so first we, so in this case it's syngas, but can be also CO2 and hydrogen reacts on copper zinc aluminum catalyst, produce dimethyl ester. Water is being absorbed by zeolite. So, and by that the selectivity to dimethyl ester has been improved. And then as soon as zeolite has been saturated by water, we can do temperature swing. We can increase temperature from the temperature of dimethyl ester synthesis to 400 degrees and remove water which is absorbed in the zeolite. Then actually, instead of doing the temperature swing, we switch to pressure swing. This is better because the problem with temperature increase, we can increase temperature relatively fast, but it takes a very long time to cool down the reactor from 400 degrees to the temperature of the reaction because of thermal inertia of the catalyst and reactor. For that, pressure swing is much better because if we want to change the pressure, it can be done very fast. We can increase and decrease pressure very rapidly, in fact. So here's the results which we obtain. So what is we start, for example, doing SIDMES test and synthesis of dimethyl ester from CO2. And you see that at the beginning, we have very high selectivity to dimethyl ester, which decreases with time as soon as the zeolite being saturated with water. But then by pressure regeneration, so we decrease the pressure from 20 bars to near atmospheric pressure, and this allows us to desorb water which is being absorbed in the zeolite, and we can restart the process and have the high selectivity to dimethyl ester, so which is close more than 80%, close to 90%. So this is the next slide show basically the concept of this. So this is the result which I show here. This is actually the results of modeling using thermodynamics. So if we conduct the reaction using hydrogen and CO2 only in steady state without ZMS, without adsorption, so it's on the left side, so we can see that the conversion of CO2 is very low because we have high amount of CO2 remains after the reactor, and a small amount of dimethyl ester is being produced, and also we have CO, which is produced by reverse water gas shift, so it's a byproduct of this reaction. However, when we add to CO2 CO, we improve the thermodynamics, so the amount of dimethyl ester increases, but still, so it's less than 50%. However, a big increase happens when we use ZMS. So we can see by doing ZMS, we can reach, so according to this modeling selectivity, so about 70% to dimethyl ester with a small amount of CO being produced. So obviously, so using ZMS has a big advantage to conducting dimethyl as a synthesis from CO2. Of course, this works with a good catalyst which need to be developed, which was developed for this reaction. So actually, this project was a part of Interact project. And finally, was realized in a pilot demonstration unit, which was built by TNO. So I took a picture of this unit, so which allows to produce dimethyl ester from CO2 using ZMS and using also optimized catalyst. Now I go to the last part of my talk, which focuses on light olefins. So light olefins, I think everybody knows, are very important platform molecules. We wrote in 2022 a review about making light olefins from different feedstocks. So you can see that olefins can be used to make polymers, of course, to make solvent, to make fuels, to make detergents, plasticizers. So have a lot of application in chemical industry. Olefins considered as building block of chemical industry. And olefins can be produced using different raw materials. First, olefins, of course, can be produced from hydrocarbons, from oil. So then can be also produced from oxygenate. Here an example of methanol to light olefins. We take methanol, which is oxygenate. It can be converted to light olefins with high selectivity. And now, so the new trend is making light olefins to produce light olefins from carbon oxide. So from CO and CO2. So it also can produce light olefins. So how we want, if we want to produce olefins from CO2, which is the topic of my talk, so there are two routes. The first route to make light olefins is called modified Fischer-Tropsch route. So Fischer-Tropsch synthesis, it's kind of old reaction, which allows producing hydrocarbons from syngas, a mixture of CO and hydrogen. However, if we work with CO2 instead of CO, we have to optimize, of course, the catalyst and reaction itself, because first, what we start with CO2, we first need to produce CO by reverse water gas shift. So CO2 reacts with hydrogen, gives CO, and then CO reacts on a Fischer-Tropsch catalyst and produce hydrocarbons. And then, of course, if we want to obtain more specifically, say, light olefins, we need maybe to do different post-treatment. For example, we can maybe use cracking and so to improve the yield of light olefins. So for that, we need to use a bifunctional catalyst, which contains, I would say, a function for reverse water gas shift and Fischer-Tropsch synthesis. The second route to produce light olefins from CO2 is so methanol-mediated route, when we take methanol synthesis catalyst and mix it with MTO catalyst, which is zoolite. So we have methanol, and then methanol is converted to hydrocarbons on, say, methanol's MTO catalyst, which is typically a zoolite. So in all this process, there are challenges. Say, first is selectivity control. So we need to obtain high selectivity, especially higher yield of light olefins in this process. The second challenge is also have production of CO, because we produce CO in, say, Fischer-Tropsch route, in the reverse water gas shift, so it will be another product of this reaction. And also produce CO in methanol synthesis route, because so it's also, let's say, reverse water gas shift, and also there are actually different way to produce CO, but CO is also a major one of the important product of this process. And also we need to think about catalyst stability. So now I just briefly show about so give more details about these two routes. So we use for developing of new catalysts, we use so-called high throughput test, which we use for this project. So we have in the laboratory, so it's RealCAD platform. So it's a center of high throughput experimentation. We have different facilities. One of them is Abantium Florence unit. When this unit, we can test 16 catalysts at the same time, using the same conditions of pressure, temperature, gas flow, and of course, in catalyst development, experiment still play an important role, and we need to do a lot of tests before identifying the best catalyst. So if we talk about Fischer-Tropsch synthesis, typically if we want to obtain light olefins, there is kind of fundamental challenge, I would say, which is due to the nature of this reaction, which is a reaction of polymerization. So of course in polymerization, it's very difficult to obtain specific product, for example, ethylene, propylene, because usually you obtain a broad distribution of product. So here I was just show the slide as the theoretical, say, distribution of hydrocarbons, which is produced in Fischer-Tropsch synthesis as a function of so-called chain growth probability of polymerization reaction. So, and the selectivity typically is governed by this probability. It's called results in so-called Anderson-Schulz-Lorry distribution. So for that reason, if the selectivity to light olefins are talking about C2 to 4 olefins in generally hydrocarbons is always lower than 60%, even say in conventional Fischer-Tropsch synthesis, which we use syngas. So we conducted a large number of tests using CO2 hydrogenation to light olefins using different catalysts, using high throughput experimentation approach. Here is a summary of the data actually. What we found, what is important, also support. We try different supports. So we use silica, alumina, and actually the best results we obtain with zirconia-based catalyst, which has high basicity, which seems to be important for CO2 activation and absorption during the reaction. What we found that there are two types of catalysts. Some of them contain, say, alkaline ions. Typically, potassium is the best. So if we add alkaline ion to this catalyst, so this is kind of, I will show this is the dependence on selectivity to light olefins as a function of CO2 conversion. So we can, as a function of CO2 conversion, we have this correlation. So we can reach, say, in the best case, about 30% selectivity to light olefins. If we prepare the catalyst without alkaline, so typically the selectivity usually is lower. So for actually the selectivity which we obtain in CO2 hydrogenation to light olefins was quite much lower than selectivity to light olefins in syngas conversion. In syngas conversion we can reach 60%. In CO2 hydrogenation we can reach about 30% on a wide range of the catalyst. So, and now the question why, what is the other product? Because selectivity so not very high, what are the other products? The other products, if you see on the catalyst which doesn't contain alkaline ions, the selectivity mostly paraffins. In fact, what happens that olefins are produced, but at the same time we have selectivity to light paraffins. What is interesting is that selectivity to light paraffins increases with conversion. So this also kind of consistent the hypothesis that paraffins can be produced by secondary hydrogenation of light olefins. On the catalyst promoted with potassium, we see that selectivity to paraffins is stable, is not very high. So what happens on the catalyst which are promoted with potassium? In fact, when we increase the conversion In fact, what happens that light olefins, they have the trend to oligomerize. It produce longer chain hydrocarbons, especially in the range of C5 to C10. So in fact, there is different mechanism of CO2 hydrogenation on iron catalyst containing alkaline ions and not containing alkaline ions. So what I showed on the slides is mechanism which we identified. So we have first in CO2 hydrogenation to light olefins. First we have reverse water gas shift reaction, which results in production of CO. This takes actually place on both catalysts containing potassium and without potassium. Then we have the chain growth resulting in formation of C2, C4 fragments on the surface. And then on catalyst without potassium, we have high hydrogenation activity, and these hydrocarbons being hydrogenated to paraffins. However, in the catalyst with potassium, potassium blocks to some extent hydrogenation activity. We have production of light olefins. However, when we increase the conversion, the fragments on the surface C2, C4 being undergo chain growth, we produce longer chain hydrocarbons. So in fact, what the conclusions that we have in this part of the work, that production of light olefins by Fischer-Tropsch synthesis, of course, may be not very efficient. So the best will be if we consider converting CO2 to light olefins. We can consider two-step. We need to separate reverse water gas shift to produce syngas from CO2 and hydrogen, and then convert syngas to light olefins, where we expect to obtain selectivity close to 50-60% instead of 30%, which we obtain in direct CO2 hydrogenation to light olefins. So then we try another route. So it's a methanol route, which combines two reactions. First is CO2 conversion to methanol, and then MTO, methanol to olefins. So in fact, we design a catalyst with two functions, methanol synthesis and methanol to light olefins. Because to process CO2 to methanol, MTO, in the industry, they require different conditions. Methanol synthesis from CO2, typically we need reaction between 2 and 300 degrees. And for MTO, we need a reaction 450 up to 500 degrees. So when we design a combined process, methanol CO2 hydrogenation to light olefins, we have kind of search for a compromise. So in this compromise corresponds to the temperature about 350, 370 degrees. So what is the advantage of the process? We have one process in one reactor which converts CO2 to light olefins. So this is the reaction which takes place. So I just plotted here. So we have hydrogen CO2 produce methanol, methanol go to light olefins, and also have, of course, reverse water gas shift reaction and methanol decomposition, which give CO. So we design also approach high throughput strategy for design of the catalyst. We tested numerous oxide catalysts for this reaction. In fact, we cannot use copper zinc catalyst for direct synthesis of light olefins from CO2, because when we increase the temperature of reaction, methanol synthesis catalyst on the basis of copper produce a lot of hydrocarbons like methane, ethane, which is not desirable for the reaction. So we design specific catalyst for CO2 hydrogenation to light olefins on the basis of metal oxide. So we characterize, so we see a lot of tests and a lot of characterization with different composition of metal oxide, which we tested. Then we prepared a zeolite catalyst. We choose SAPO34 zeolite because this zeolite has a small pores and very selective to light olefins in MTO process. And we have different samples with different crystallite size of the zeolites SAPO34 and with different amount of acid site with different strength. So we try to optimize both, optimize function for methanol synthesis and MTO in the bifunctional catalyst for CO2 hydrogenation to light olefins. So they have also different acidity, as you see, which we measured by TPD of ammonia. And then what we found this kind of general correlation between selectivity to CO2, selectivity to light olefins and amount of CO2 converted to hydrocarbons. So we consider a little bit separately production, methanol synthesis, MTO, and conversion of methanol to light olefins. And we see this correlation that basically if we increase the conversion, so the selectivity to light olefins drops, but in the best case, we can obtain selectivity to light olefins, say about 60 up to 80%, say 60-70% we can obtain in this process. So, and then we try to see which parameters of the catalyst play a role on this selectivity to light olefins. So the first parameters which we found is the crystallite size of zeolite. So in fact, when we use smaller zeolite with smaller crystallite size, these curves, you see, it's much located much higher compared to the catalyst which contains a larger crystallite. So in fact, if we want to make light olefins with high selectivity on this composite catalyst, we need small zeolite crystallite size. So the second parameters is what we was found, which is say much more also has much smaller effect, is acid site density and acid site strength. So to obtain high selectivity to light olefins in this process, we don't need very strong acid site. So we need acid site which has so less acidic zeolite, increased selectivity to light olefins. So it means that by optimizing first the zeolite crystalline size and zeolite acidity, when increase the selectivity to light olefins, here I see by about say maybe 20%. So now I will go to the conclusions of my talk. So, and I would like to summarize. So we have several examples: CO2 conversion to hydrogenation to valuable products. So was formate, dimethyl ester, and also light olefins using Fischer-Tropsch synthesis and methanol route. So, and what is it? But still, there are some challenges and then possible solutions for CO2 hydrogenation to valuable product. In terms of challenges for all this process, if we do, say, economic analysis, what is the most important for hydrogenation? We need cheap and green hydrogen. Because now the hydrogen which is produced by electrolysis is expensive, and because of that, the product which we produce from CO2 hydrogenation are expensive compared to market solutions. The selectivity, depending on the process, in some process, for example, like Fischer-Tropsch synthesis, I showed you that selectivity to light olefins is insufficient for industrial production of light olefins. So it can be improved, obviously. And also we have to think when we conducting CO2 hydrogenation to different products, we need to think about thermodynamics, because for many reaction, thermodynamics is kind of difficult. And there was an example how we can improve thermodynamics, for example, by combining dimethyl ester synthesis with absorption of water. When we remove water from the reaction, we increase basically the productivity of this process. And of course, we need to think about the cost of different CO2-based fuel and chemicals relative to the existing market solutions. What can be solutions? So the first, I would say, if we want to decrease the price of the product produced from CO2 hydrogenation, we need to find new technologies for production of sustainable hydrogen. Then, of course, the development of catalysts operating at lower temperatures, low energy consumption, increase in product selectivity. So basically, this is the work that we are doing. And also think about not only about catalyst, about chemical and engineering strategy to improve thermodynamics. Here, an example, for example, what was given about maybe chemical looping, transient epuration, sorption, enhanced reactions. And also, in addition to thermocatalysis, there is also a fastly developing area of electrocatalytic process for CO2 reduction, when we can produce, for example, use CO2 in water and produce valuable product from CO2 in one step. So there are a lot of publication on this topic. Of course, this area needs a little bit more maturity. And now I would like to thank you, my colleagues. So Vitaly, Mirella, Robert, who contributed to this work, also PhD students and postdoc. So actually most of them already had defended PhD. And we also have collaboration with University of Ghent. And also it was an example of nice industrial collaboration with TNO in the Netherlands. Also have funding from Interreg. Actually, we have already Interreg from 2C, with which we collaborated with Netherlands, with Belgium, and also with United Kingdom, which is at that time also collaboration Psyche project, which is also a very fruitful project, which Franco-Belgian collaborations, takeoff European projects, so and INR, French National Energy for the Research. So I would like also to thank Interreg and OBIWAN project, which now we're just starting, and I hope we'll have a large number of nice results, and all our partners. And I would like to thank you for your attention.